Good morning, one and all. Today we are going to discuss the equivalence of NFA and DFA. In the previous class, we discussed what is an NFA and what is a DFA and how an NFA can be converted to a DFA, and any DFA can be any NFA can easily be converted to a DFA. That means an NFA is having more than one outgoing transition for the same input symbol, but in DFA it is deterministic. That means only one outgoing transition, definitely one outgoing transition is there for the same input symbol, and it is easy to construct NFAs, and then converting that to DFA is very easy, but constructing DFA straight away is a difficult task. So for difficult problems, what we do is initially we are constructing NFA, then we are converting that to DFA, then writing the program for that. Okay, now the language accepted by a DFA is regular set, and language accepted by NFA is also regular, and that is language accepted by both are regular sets. Now we have to prove that both are equivalent. That means this is the proof, and here yesterday we discussed how this is done for a problem, and now this is theoretical. That means here this is M is equal to Q sigma delta Q0 F, and this is for an NFA. And suppose that you have an NFA like this. Here M is having the set of states, sigma is the input alphabet, delta is transition function, Q0 the start state, and F is the set of final states. And now you are going to have another automaton which is deterministic, and there we are having Q dash, sigma, delta dash, Q0 dash, and F dash. Okay, that means here we have another set of states. Unlike this, here we have another set of states. Input alphabet is same. That means if the input string is binary, then for both of this the input string is binary. If for both of this, if the input, that means we are going to process a string. This is the string, and the set of permissible symbols in the string is called sigma. That means for both of this, those are same. That is the same. And delta is a transition function. Delta is different. Q0 is the start state, and Q0 dash, the new start state, is represented by Q0. That means Q0 within square brackets. That is, this is different from this. Q0 dash is Q0 within brackets. That means if the start symbol for the NFA is Q0, and the start symbol for this will be Q0 within square brackets, and F dash is a new set of states, and that also we'll discuss later. Now, previous class I demonstrated how the relation between Q dash equal to 2 raised to Q and Q. That means here, suppose that this Q, the NFA is having 3 states, Q0, Q1 and Q2. Then this Q dash is having how many states? You have to take the power set of Q. That means 2 raised to Q, and 2 raised to Q is having how many elements? That means here we have n is equal to 3. So what is 2 raised to 3? That means 8 elements are there in the power set of Q, and each of the elements of the power set represent one state in this DFA. But all those states are not reachable. That's why you can eliminate some of the states. Anyway, at most you can have the power set. That means 8 elements. If you have n is equal to 3 here, you can have at most n elements. Okay. Now Q0 dash is represented by this, and now I told you about Q dash. Sigma is the same. Q0 dash is Q0 in brackets, and F dash we'll discuss later. That means I'm going to discuss delta dash as well as F dash. Here one state in M dash corresponds to multiple states of M. One state in M dash corresponds to multiple states of M. For example, suppose that Q is equal to, say, Q1, Q2, say Q3. Then suppose that Q0 on accepting, this is Q0, Q1 and this is Q2. And suppose that Q0 accepting 0, it is staying in the same state Q0 as well as switching to state Q1. That is, upon this, suppose that Q0 is a start state and Q0 is having a self loop as well as on 0 it is switching to Q1. That means this is a single state of Q0 and Q0 upon reading 0, what will happen? It can either stay in the same state Q0 or it can switch to Q1. That means delta of, that means the original delta of Q0 upon reading 0, what will happen? It is equal to the set Q0, Q1. That means Q0 upon reading 0, it can either stay in the same state Q0 or it can switch to Q1. That means Q0 upon reading a 0, in the NFA there are two controls. One is going to Q0 and the other is going to Q1. When you are converting this to its equivalent to DFA, what will happen? This thing, this Q0, Q1 represents a single state. That means delta of Q0, this is the start state, upon receiving 0, what will happen? This is equal to the state Q0, Q1. Q0, Q1. That means this Q0 and this Q1, those two collectively forms a single node here, single state here. That is why we have the statement one state in M dash corresponds to multiple states of M. That means multiple states of the NFA is encoded as a single state in the DFA. For example, here Q0 and Q1, that means multiple states are encoded as a single state in this DFA, single state in the DFA. Okay. Say, now the set of states Q1, Q2, etc. up to Qk, that means this is corresponding to M. That means in the NFA, suppose that we have a number of states Q1, Q2, Q3, etc. up to Qk, that is represented by Q1, Q2, etc. up to Qk within square brackets. That means everything within square brackets. If a state is represented by like this, that represents a DFA. That represents a DFA, and the states of the NFA are Q1, Q2, etc. up to Qk. These are all different states. Q1, Q2, etc. up to Qk are different states, and all those states are collectively or multiple states of the NFA is equivalent to a single state of the DFA. Multiple states of the NFA. Then, for example, in our previous example, Q0 and Q1, we are going to collectively or both of them represent a single state of the DFA. Likewise, here these states, that means Q1, Q2, etc. up to Qk, these are all different states of the NFA, and those different states of the NFA can be collectively represented by a single state of the DFA, and that is denoted by this. That means Q1, Q2, etc. up to Qk. Here there is no separation. Here you have to write Q1, Q2, etc. up to Qk and put square brackets on both sides. Now, third one is delta dash of Q1, Q2, etc. up to Qk within square bracket. That means this is a single state of the DFA. This is a single state of the DFA, and that on receiving an input symbol A, what will happen? That means this delta dash is the transition function for the DFA, and if that is applied, that means this is a single state, and in that state if it is accepting A, what will happen? It will switch to another state P1, P2 etc. up to PR in square brackets. This is a single state, this also is a single state. If what will happen? Delta of Q1, Q2 etc. up to QK1A, that means in the original NFA, if delta is applied to Q1, delta is applied to Q2 on A, delta is applied to Q3 on A, and delta is applied to QK on A. These are all different states of the NFA. You are going to apply what is delta of Q1, Q2 etc. up to QK on A means delta of Q1 on A union delta of Q2 on A union delta of Q3 on A union etc. up to delta of QK on A. That means if the union of all those is P1, P2 etc. up to PR, these are all different states. That means delta dash is this one if delta is this one. That is our assumption. That means delta dash of this single state which is represented by Q1, Q2 etc. up to QK1 A is equal to P1, P2 etc. up to PR within square brackets. That is also a single state. That means this state is switched to this after accepting A. If it has to happen, delta of Q1, Q2 etc. up to QK1 A should be the states P1, P2 etc. up to PR. These are all different states. Here, how many states are there? Q1, Q2 etc. up to K number of states are there. You are going to apply what is the transition for A for Q1, Q2 on accepting A, Q3 on accepting A up to QK on accepting A. What is that? So take the union of all those and let it be P1, P2 etc. PR. Okay. These are different states of the NFA and these are different states of the NFA. But this is a single state of the DFA. This also is a single state of the DFA. If this has to happen, this should happen. That means this is the correlation between NFA and DFA. Here we are going to prove this. That means in theory of computation, most of the theorems are proved using mathematical induction. In mathematical induction, first of all, we have to prove that it is true for the basis. Then we assume that it is true for the induction step, and finally, we using the inductive hypothesis, we are going to prove that it is true for n is equal to some k plus 1 or n is equal to n plus 1 etc. Okay, you know that. Here, in general, we have to prove that delta dash of P1, P2 etc. up to PR on X. Here we have A. A is a single input symbol, but here X is a string. X is a string. That means if delta dash of P1, P2 etc. up to PR on X, that means here delta dash, this is the DFA, and then this is the transition function for the DFA. And if you are applying P1, P2 etc. up to PR, that means this is a single state, and from that state on accepting X, that X can be for the basis, that X can be epsilon, then X is a string which is having length n, and X is a string which is having length n plus 1 etc. etc. That means this X is a string, and this on accepting X is equal to this if this condition is satisfied. That means delta of P1, P2 etc. up to PR on X. That means what will happen? Suppose that this X is having set 10 elements, then P1, P2 etc. up to P1 for the first element, second element, third element. That means you have to do all these things and take the union of those two. Then you get Q1, Q2 etc. up to Qj. That means we have to prove that if this has to happen, this should be true. Okay. Then here we are going to use induction on the length of the input string. Here, length of the input string. Here, for x is equal to 0 or modulus of x is equal to 0. That means if the length of the input string is 0, we have to prove that this is true. That means this is the condition you have to prove. And then we assume that this is true for modulus of x is equal to n. And once it is true, we will prove that it is true for modulus of x is equal to n plus 1. So here for the basis x is equal to epsilon, that means length of the input string is null. That means without accepting anything. That means if your finite control is in start state q0, what will happen? X is equal to epsilon means it is accepting anything. It is not accepting anything. That means input symbol is nothing, null. Then what will happen? That q0 is remain in the state q0 itself. That means hence this is true. That means p1, p2, etc. up to pr on epsilon. What will happen? It will stay in the same state. Then p1, p2, p. This is a single state. P1, P2, etc. up to PR on epsilon is equal to Q1, Q2, etc. up to Qj. This is P1, P2, etc. up to PR. Then P1 on epsilon, P2 on epsilon, etc. up to PR on epsilon is P1, P2, etc. up to PR on epsilon. Okay. Hence, this is true for the basis. Then, in the inductive step, we assume that this is true for modulus of x equal to n. That means the length of the input string is equal to n. The length of the input string is equal to n. That is assumption. Assume that it is true for modulus of x is equal to n. Then our assumption is this is true. That means delta dash of p1, p2, etc. pr on x is equal to q1, q2, etc. up to qj if delta of this equal to this. That is our assumption. Our assumption is this. And next, in the inductive hypothesis, if this is true for strings having length n, our assumption is this is true for all strings which is having modulus of x is equal to n or the length of the input is n. If this is n, it should be true for strings having length n plus 1 also. We have to prove that our assumption is this is true for modulus of x is equal to n. Now we are going to prove that this is true for modulus of x is equal to n plus 1. Okay. Here we know that modulus of x is equal to n. Now P1, P2, etc. to PR on XA. XA is having length n plus 1 and this is a single state, and on receiving x, our assumption is on receiving x, this is going to Q1, Q2, etc. up to Qj. That is our assumption. Okay. Now P1, P2, PR on XA. That means one more symbol is coming. One more symbol is coming. That means after the input X, there is one more additional symbol A. That is why we are having length n plus 1. Okay. That means delta dash of P1, P2, etc. up to PR on XA is after receiving X, where do that reach? Where does it reach? That means delta dash of P1, P2, etc. PR on X. On X, it reaches some destination, and after that, it is receiving A, and that is delta dash of Q1, Q2, etc. up to Qj on A is equal to, that means delta dash of P1, P2, etc. up to PR on X is, as per our assumption, that is Q1, Q2, etc. up to Qj. And that on accepting A, what will happen? It reaches R1, R2, etc. up to Rp if this has to happen. If this has to happen, then delta, that means for the original delta, that means for the n of A, Q1, Q2, etc. up to Qj, these states on A is accepting, or that will move to these set of states. That means these set of states on accepting A, that will move to these set of states. Okay. And from this is statement number 2 and this is statement number 1. That means delta dash of P1, P2, etc. up to Pr on X is equal to the Q1, Q2, etc. up to Qj if delta of P1, P2, etc. up to Pr on X is equal to Q1, Q2, etc. up to Qj. That is our assumption. Now, delta dash of P1, P2, etc. up to Pr on Xj is equal to, that means after X it is receiving one more symbol X, and after receiving X it reaches where Q1, Q2, etc. up to Qj, and after that on A it reaches R1, R2, etc. up to Rp. If this has to happen, then delta of Q1, Q2, etc. up to Qj on A is equal to R1, R2, etc. up to Rp. That is our second assumption from 1 and 2. From 1 and 2. What is our assumption here? This is the assumption and this is the second assumption. From these two, we deduce that delta of P1, P2, etc. up to Pr on X is equal to R1, R2, etc. up to Rp. Okay, that means delta of P1, P2, etc. up to Pr on X is equal to R1, R2, etc. up to Rp, and that means hence the theorem is proved and the language accepted by the NFA is the language accepted by M dash. With this, we have proved that the language accepted by both NFA and DFA are equivalent.